Hey, top of your life's math and history, and today we're going to look at orbital velocity because today is New Year's Eve, which means tomorrow is January 1st, 2022, and Earth has made one revolution around the sun, meaning 1 year has passed. So what we're going to be doing is trying to find out what the orbital velocity of a space station is. And it's on a word problem. So, Henry Stickmin is trying to get to the top at space station. The station is 400 kilometers above the ground in altitude. And how fast is a space station floating through Earth's orbit? So what we're going to be doing is trying to find how fast does that space station go around Earth meters per second.
No. Well, just shoot it down.
So, that is what orbital velocity is. Trying to find how fast that space station is going. So, there's a formula that we're going to use to help us get to our answer. That formula for orbital velocity is the velocity is going to equal the gravitational constant multiplied by the mass of the Earth and divide that by the distance from the Earth's center all the way to the space station. So, after we do that, we find the square root and find our answer in meters per second. But wait, what is the gravitational constant? What is the mass of the Earth? And what is the distance from the Earth's center? What are those definitions? So first, we're going to understand what those three things are. Let's look at the gravitational constant first. So, the gravitational constant is represented by the letter G, and it measures the distance between the two planets and the masses between the two planets. This is actually discovered by Isaac Newton, but there's another formula that he uses and also that we use that helps us understand what gravity is. Gravity is the force trying to pull things together or pull you down. When you jump up in the air and you come back down, that's gravity because Earth is trying to pull you back down. What goes up must come down. But that is if you see it on Earth and other planets, but if you're on the surface of the planet, we're talking about outside the planet or outer space. So, Newton actually made a formula that can help us understand what gravity is and what force is. This is called Newton's universal law of gravitation. So, the force between the two planets is going to equal the gravitational constant, which is our measurement. The mass of the first planet, multiply that by the mass of the second planet, that we divide by the distance between the two planets by their center point, the center of the planet. So pretty much, the mass and the distance are going to be two effects on how hard the planets are pulling at each other, or how hard the gravities in between are making them want to come together. Here's an example when we increase the mass versus making the planets more farther apart from each other on a planet simulation app. So, increasing the mass or decreasing the distance between the two are going to make the force and the gravity stronger. So, the number that we use for the gravitational constant is 6.673 multiplied by 10 to the negative 11 power n multiplied by m squared per kilograms cubed. So, we use that number and put that in the gravitational constant that measures the gravity and the forces between the two planets. Now let's measure and understand the mass of the Earth. But what is the mass of the Earth? When we calculate mass, it's actually not your weight. Weight and mass are two different things. Your weight is actually cheating because the gravity that's pulling you down is causing you to get your weight. Mass is totally different because the mass refers to an object and how many particles are in it. That's why we use kilograms and other parts of the metric system for the mass. With this block right here, or this square, if you have a gold block from Minecraft and put it on Earth, it would weigh really, really heavy. But if I put that on the moon, if we ever go to the moon, it would feel very, very light because the moon does not have a lot of gravity as the Earth does. But the particles inside that gold cube are still there. So pretty much, we use kilograms to measure the mass. It may feel different, but all the particles that are inside, the number stays the same. So the mass of the Earth in kilograms is a very, very big number. That's why we're going to use exponents. And that number is 5.98, multiply that by 10 to the 24th power in kilograms. So, Earth has a lot of mass. A lot more mass than your car, the moon, yourself, a school, pretty much anything except bigger planets bigger than Earth. So, this is the mass for Earth. We'll be using that in our formula later. So that is the mass of Earth. Now let's explain the distance from the Earth's central. But why is it used as the letter R? Why can't we use the letter D? Here's why. If you have a space station right here, and you have the planet Earth right here, that space station and Earth is going to be apart from each other. So we have to measure the distance to get to Earth. But we measure the radius or the middle because that space station is going to orbit Earth in a perfect circle. So pretty much it's going to orbit Earth at a perfect circle, and the distance between the center point and the space station is going to be like a swinging bat, like the radius of a circle when you calculate for area. Area equals pi r squared. So that radius is actually going to be here to here. So it's swinging like a circle, like a hand clock. Here's an example. If that blue thing in the middle was Earth, and the red line is the distance between Earth and its center point and the space station, which is gray, then it is gonna look like this. So, pretty much, the space station is orbiting Earth, but that red thing that is going around in circles is basically the radius of the circle for the orbit. So, when we measure the space station to the ground, we also gotta measure inside the planet, because we're looking for the central part of Earth. We are looking from, here's the space station. What we're measuring easily is from here to the ground. We have to look at what here, the ground, to Earth's middle is. And when we find that distance, the Earth's distance from here to here is 6.38 multiplied up by 10 to the 6th power in meters. And from here to there, we said the space station, the Top Hat space station, was 400 kilometers. So we are going to have to add the two. But the problem is they're in different measurements, kilometers and meters. So we're going to have to find a way to get them the same. Then we can add to get the space station and the central part of Earth, find the distance between the two. So let's convert them to meters, since this is already at meters. So 6.38 multiplied by 10 to the 6th power, we have to do the exponent first, because it's order of operations. So we have 6.38 multiply that by, how many zeros are 10 to the 6th power? Is 1 million. So 1, 2, 3. 1, 2, 3. So this is basically a million. 10 to the 6th power is 1 million. And when we do that, so 6.38 multiplied by a million, we get 6,380,000. So that is the distance in meters. But wait, we also have to have 400 kilometers converted into meters. So, and to do that, kilometers or kilo means 1,000. So we're going to have to multiply that by 1,000 to get into meters. So we can say 400,000. So that is how many meters are from the space station to the surface of the Earth. So when we add the two, when we add 400,000, we get 6,780,000. Wow! So that is the distance between the space station all the way to the center of the Earth's core. The really center, and that's the distance between the two. So that is why we use the R as the distance, and from the Earth's central. We had to calculate the distance from the space station to the surface and the central to the surface. Add the two up and get our distance. 6,780,000 meters apart from each other. So we have every information that we need. Let's insert those information into the formula and square root it and see what our orbital velocity is. So our gravitational constant is going to be 6.673 multiply that by 10 to negative 11th power. Then we also have to look at the Earth's mass. That is in kilograms. 5.98 multiply that by 10 to the 24th power. Then we're going to have to divide by our distance between the Earth's central core and the space station. And that is 6,780,000 meters. And when we do that and square root that, we'll get our velocity in meters per second. How fast is that space station going? So you will need a calculator for this. First, when you grab your calculator, clear it. Then type the gravitational constant first, then multiply it by 5.98, multiply it by 10 to the 24th power, then hit equals. Then when you do that, divide that by 6,780,000, and when you hit equals again, it gives you a different answer. Then when you find the square root of that, you get your velocity, your orbital velocity. So let's start doing that. So, when we do that, we get an answer as 7,671 meters per second. That is how fast the space station is orbiting Earth at. Meters per second. That is very, very fast. And that is around how fast the ISS orbits the Earth. Around 7,670 meters per second. If the space station was exactly at 400 kilometers above the surface of Earth. And this formula would only work if the space station had a perfect circle as its orbit. The Top Hat space station is orbiting Earth at 7,671 meters per second. And that is the orbital velocity. The orbital velocity for Earth is 30 meters per second, orbiting the Sun. And by 12 o'clock midnight, that is precisely when Earth makes one revolution. I hope this video has helped you. Thank you for watching Top Life's Math Industry. Like and subscribe. And to end the video, let's see the ball drop in New York City, Times Square, for a Happy New Year!